Yes, 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 yes. I know, I know, I know. God, I hope my camera's not on because it'd be a problem. So anyway, I finally have a decent looking tuning cavity built. Um, but according with talking about my project, it's a little bit large, and all of the measurements that I've taken with it uses up the entire space of my enclosure, which is 15 inches, and sets the beam splitter all the way to the end of the, um, yeah, the light unit. There's like two units. There's the light unit, which is 15 inches high, and the dark unit, which is only 12 inches high, which is not a big deal because the final signal goes from the light section to the dark section. So it shouldn't be a problem. I'll just have to do a little bit of redesign consideration when it comes to setting that up. So the beam splitter that I am using, or there's like three of them. There's like a glass, there's a plexiglass, there's a plastic from the CD case, which is pretty good actually. Um, the microscope slides. I'm having a melted snack here. I seem to lose power. But the plastic one, surprisingly, that thing splits really good. But when you adjust it, when you look at it, you can see two beams, which is not really what you want. You're seeing a reflectance of the second beam up against itself, and I was thinking I could get away with it, but I don't think I can. So what I'm going to do is I'm going to watch a few videos. Again, which I totally wasn't planning on doing, honestly. um, but the need has arisen, and I'm going to go to my paint setup and talk about where these beam splitters are going. I thought I had. What am I doing here? It might be helping with paint. That's not it either. Yeah, let me just open this one up here. Maybe I can talk about it with this particular image. Because I need to acquire this product, and I found some decent ones. They're like 25 bucks, and I got a reprieve on my property insurance. So I've got some extra money, and I had to make a double payment on my Amazon anyway. So there's some money in there. But if I go to, let's go to my paint here, and don't know if that's adjusted properly or not, but we can fix that. It's a different picture of some sort. But anyway, so I'm going to have another setup, and I think I'm certain that it requires another beam splitter. So I've got um, this tunable grating. Oh shit. Now I was planning on using the grating going into the beam splitter. Now I can't do that because hmm let me just go ahead and so there's like a mirror, and the light comes in from the top, hits the mirror, and goes into this secondary mirror, which goes into the beam splitter. Well, I am deciding, I'm going to use the same size line. I'm deciding to use the same beam, and I don't know as far as the distance calculations and so on and so forth. Um, no, I think. Oh, actually, we're not using an optical. We're using what's called a plate. Oh, yeah. So actually, yeah, we're using a plate, but I'm going to go ahead and just throw the beam splitter, that splitter triangle in here. So that's a mirror. There's going to be another mirror down here, which, I don't know if the orientation is correct. And we're going to use, let's use this brown color. So the brown, the light comes down to here. It bounces off of that mirror and goes through here. And then there's going to be another beam splitter. Well, that's not supposed to look like that, but what the hell. And then down at the bottom, there will be a calibration mirror. That mirror goes back, so that mirror goes back through the system. Now let me think about this. I don't want the reflected beam to go all the way back through the system. The only other option, like if this is like, if it's like this, fuck, if it's like this, and it's like this, and it goes up here like this, and it's supposed to go. Okay, if I'm looking at the longitudinal axis, okay, that is different. That's not correct. So let me go here. Get rid of this crap here. So that line needs to be like so. Okay, so over on the left, I could just put this damn triangle. Everything's gonna look combobulated though. So over here, oops. Yeah, over here would be the cylinder. And I could just put a little thing in here like so, and another one like so, and then a line. that's a camera, and so the light goes through the beam splitter here to the camera. Oh shit, it's going to reflect upwards. See, this is why I gotta do this, because hmm. 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 Well, I'll be a monkey fart. So my original plan was to set a light to electrical detector on the bottom. If I set it on the top, and we'll use a mirror. Let's see. We'll use a mirror as a calibration mirror. And all this other crap over here, this is all um, this is separate over here. This is not part of the system. Damn, I need another drink. So the light, the translational light coming from the tube will reflect up to here. And okay, so actually, no, wait a minute. Wait, hold everything. I just realized something. I could put it on the bottom, because what's going to happen either way is that the reflected beam, when it comes back down here, no matter what I do, is going to get reflected back into the tube. However, okay, so it goes back into the tube, and I'm wondering if this mirror is pointed in such a direction, it's going to end up going all the way back to the source. Or is it? It's going to reflect here. Hmm. Do I have another? Well, I'm going to have a lens set up. There'll be a lens set up in there. I'm thinking in terms of calibrating that mirror that's on the top. It can be either on the top or the bottom, because it's going to end up going back through that where it came from, which I didn't really want to have happen. And that's a beam splitter, by the way. It seems to me there should be a way to avoid that. If that's the source, and I do it at the bottom, it's still going to come back and reflect. So if it reflects back was thinking that that other mirror is a beam splitter. So if, let's say if I have, let me do this yellow again. And we'll just do this. This would be like 3D type of thing. And this is my cylindrical tube. And I'm forced, because of the way the beam splitter is rotated, I'm going to have a reflected signal back through that tube regardless. Now, if I use a beam splitter on this other section and I change the beam splitter, I've got a light coming from the top that needs to go. Okay, so what if I do the beam splitter like this? The light comes down, it goes down through here, and then it hits this mirror, and then it goes back up to here and out to here. Now, instead of the transmitted beam hitting a mirror and going through the tube, the transmitted beam is going through a beam splitter, and then it's going to be reflected off of the beam splitter. It's going to go down through the beam splitter, hit the mirror, come back up, and be reflected through the tube. The reason for putting a beam splitter here is to prevent this other reflected beam from going back into the source. So if I do this line, and now I have a line going to here, that line is actually going to go straight through here, now there is a wall there. There is a wall there, which I can make it black. I can put something in there to absorb that light energy. And then it won't go back into the beam splitter and back up into the source. So this arrow will go down here, and then it will go back up to the beam splitter, and then go back the light comes up, the light comes up like so and gets absorbed. The incident light comes from the source, which is reflected, and then it hits the beam splitter. It's going to go through oopsie daisy. It's going to go into the camera. Alright, so the source signal comes down to the beam splitter, hits a mirror, reflects off the beam splitter, goes into the camera, goes down to a mirror, which I'm not really showing just yet. It's damn it, what the fuck is going on here? Right, so there's a line, put a line down there to represent this mirror. And so the yellow line goes down like so. That's the source beam. Now that mirror is in the wrong damn orientation. It needs to be like the original picture. I can't fucking do anything right. Damn it. Let me draw. Let's draw this one here. We'll make it a thicker line, maybe. It needs to be like this. Okay, so the beam splitter on the bottom. So let's put this in here and make this a little bit more visible. Now, the source signal goes through the beam splitter to the camera. Fuck. It's getting reflected up with no mirror. Damn it. If I use the other one, it gets reflected down and back to that mirror. But the camera... Oh, wait a minute now. I'm thinking in terms of the dark red one. Source signal comes in, hits the dark red one, goes down, and then it goes up into infinity, etc. No, it does not. It goes through the beam splitter, and it goes down and back up. So, okay, so I've got a source signal going to the camera. The first pass of the source goes down to the first mirror, up to the beam splitter, across to the second beam splitter. We're using the back one now. One goes to the camera, one goes down to the mirror, back up to the beam splitter, gets reflected back to the first beam splitter, which gets reflected back to the mirror. Once the mirrored source signal gets reflected back to the first beam splitter and mirror, it'll go back up to the beam splitter and out to the camera. So there is a tuning source signal from that configuration. Because I've got the source, which is reflected the first time, and I've got the reflection from the mirror, which goes to the beam splitter, goes to the beam splitter, goes down. Yes, so let me just go ahead and do this again and make this large. So I think the beam splitter that I want is going to look like this here. No, it's actually, I've discovered what's called plate beam splitters. They're just plates. But I'm using the triangle to denote what's going on here. And so let's make a green check mark. And we'll do like this. And then we'll make a red X over here, because that's not the correct one. The one on the right is correct. The one on the left is is incorrect because it has to bounce off a mirror. The reason for the second mirror on the left is to calibrate this particular interferometer source. Now, the only other information I don't have is distances. I think those, whatever the hell it is, they're going to be the same. You have to have so um, the second mirror underneath that beam splitter is actually going to be a transducer. So what I have is I have a source signal that is beam split going transversely or translationally through the light beam at 90 degrees. And that light oh shit, you know what? Damn it to hell. Fuck. Oh shit. You know, I only have oh, I hate light. Let there be light. So it goes translationally at 90 degrees through the light beam, bounces back and forth between the two mirrors. That reflected signal goes into the camera. That reflected signal plus the source beam, the beam splitters and the mirrors are aligned such that you get one signal into the camera. Once the second mirror is aligned, that mirror is replaced with the transducer, which is which could be an LED, it could be a solar panel, it could be whatever I'm planning on using to collect the light and convert it to an electrical signal. I'm thinking an LED because I was going to do something with my LEDs tonight, and all of a sudden it's freaking late again. Um, but now I'm realizing something. Any information that comes translationally off the light beam, there's a 360-degree um, let's use this one here. So let's use green to note the light beam, and then back to the line. And so like if we go like this, wait, no, let's use red. We'll make an axis like this, and then we'll change that line and change it to green. Well, actually, no, it should be gray because gray is our time denoted axis line. And so now we go here. So what happens is the photon, it moves spirally. Okay, it moves such that it's, oh shit. It moves in a circle, but the circle moves forward, okay, in time around this axis. And so what I'm doing is I'm sending a light beam transversely through the system, like so, which was supposed to be a straight arrow and it wasn't, to interfere with the light beam pattern and create an interference pattern on the other side, which probably it may need to have a slit. Let me just put a couple of dark gray lines here. I don't know if that's true or not. It'd be like something like that. And then you have another line here. I have no idea, you know? Let's go here. You can't see it very well. So that's a slit. And the reason for the slit is to create an interference pattern. But the problem, wait, this is circular in nature, isn't it? But still, you have a signal that, let's see here, it's like that. Okay, so you've got a vertical. Now this is a little different because it's like a sine wave that's vertical. And then on the other axis, in phase with that, you've got, I'll make it a little bigger just to be exaggerated. You've got the magnetic line. Now, theoretically, the magnetic line is not something that's going to be visualized. It's only the electrical. So maybe I'm okay here if I'm 90 degrees to the electrical portion of the light beam. But if I'm not, the only solution to that problem is to take this slit and rotate it. That would mean rotating like everything, you know? So then that option is impossible. The only other option would be to rotate the light beam that's coming through the system. Now polarizers only illuminate, they don't rotate the light beam. So how do you know how the light beam is oriented when it comes through the system? It just makes an assumption that the electrical portion of the light beam is up and down instead of 45 degrees or 30 degrees or whatever hell degrees it wants to be. What if, okay, so there's a crystal, and let's do this picture here. There's a crystal, and I don't know if I don't think this is the correct orientation. It would be like flat, wouldn't it? This is going to be a really difficult picture to draw. So this is like a rectangle here. Yeah, it's not too bad. It's not centered like where it's supposed to be. Well, this crystal, if the crystal is centered on the axis, if I just draw another line here, actually it should be gray. So, okay, so let's just assume that it's centered on the axis. And then what you could do, you can take this crystal. This is the magic. This is where the magic happens. You can rotate the crystal centered on the axis. And maybe you can rotate that electrical signal. And you can verify that by measuring the strength of the electrical signal coming through to the camera translationally, or not to the camera, but to the transducer. End of story. All right, so I'm going to save this. This is going to be LW beam splitters. So I've got one beam splitter coming to the source, going down to the second beam splitter. That's a total of 2. That one goes down, so this one over here That's a beam splitter. And that's a beam splitter. So there's two translational beam splitters. And two vertical beam splitters. That's a total of 4. That figures. There's 1, 2, 3, 4. You have to have 4 if you want to do the translational test at the same time. So now the problem, when it goes through the first beam splitter, you've got a 50-50 loss of transmission. So then I'm working with 50%. I go through the second beam splitter on the left. Now I've got 25%. So going into the third beam splitter into the translational camera, I'm looking at a 25% visual signal. Maybe that's not no problem. 50, 25, no, 12.5%. The reflected signal, you know, it really shouldn't matter because it's going back and forth between the two beam splitters. It should be the same level. It should be 12.5%. Or even if it's less, it's going to amplify the signal. But then, no, wait, it's not going to amplify the signal because I'm going to put in my transducer in there. That second mirror is only for tuning. Unless if I was to put another beam splitter in there and reflect the signal into the transducer so that that signal could go back up into the camera. But that really wouldn't make any sense. The purpose of the beam splitter setup is you tune, okay, so you tune the camera and you've got to have a signal that goes to the transducer, and it's gonna end up reflecting back, and you don't want it reflecting back to the source, so you have to put another beam splitter in there. So there's 1, 2, 3. There's 1, 2, 3, 4. There's 4 beam splitters. All right. So let's go ahead and listen to these videos, and then so on and so forth. Let's see what we got here. YouTube. All right, so maybe that was some kind of whatever that was. Okay, there's the plate glass one. I don't know what he's doing there. Add fog to see the laser. Yeah, he's just he's smoking on it. Yeah, okay, that's fine. Okay, hold the fort, people. Just hold the fort. This guy acts like he really knows what he's talking about, and I gotta get a drink to listen to this one. I love misinformation. Yeah. My name is Information Mac. Ooh, yeah. Gimme, gimme, gimme. I want it to be October. I want my candy. I got a donut I could munch on. Fuck. I gotta go eat a donut, don't I? I don't want remember seeing it though. How was it? I guess. Now this guy really knows what he's talking about. Ah, if I want to make two dots, I can just put a mirror in there and reflect it out the beam and I got two dots. They don't call me Dottie for nothing. I get a kick out of some of these videos. Even these people at the university, all right? No gloves, no hairnets, no whatever in this $1 million optics lab, and they're handling this shit with no gloves on there. I don't even want to talk about it. Okay. Yeah, you got two beams, but it's not a beam splitter, Bubba. It's only a mirror. Hello. Oh, wow. Wow. Okay, you show me how it works. Oh, yeah, yeah. Okay. Yeah, there you go. Yeah, yeah. Yep. Yeah, yep. Okay. Mm-hmm. Okay. Okay, he's only got 52,900 subscribers. All right. Yeah, it's okay. Yeah, okay. So the problem with that is that you don't get one beam coming off the reflected side. You actually get two beams. Shut your pie hole. You get two beams because the plastic is made of uh, two sections. It's not hollow in the middle, but it has a front surface and it has a back surface. When the light goes through, it hits the back, it hits the front surface, and it hits the back surface, and it's reflecting off of two surfaces onto the wall on the right. But of course, he doesn't say that because he doesn't know what he's talking about. He only knows half of what he's talking about, but the other half, you don't know. When you talk about stuff like this, in a layman's term, it's okay. It's nice. But when you do something like what I'm doing, and I'm not doing perfection. I'm just doing it's science. It's you've got to know everything that you're supposed to know when you're doing a test so that you can replicate it, and you're trying to prove something, you're trying to collect information. And if you got two beams being reflected, one beam is going to interfere with the other one, and it's going to make your noise just intelligible. You won't be able to read it unless there's a way you can get rid of the back reflected beam, which is impossible to do because unless if you have a beam splitter that's a foot deep, maybe you could do it with that, or 6 inches deep. But I don't have that kind of, whatever. So you have to have the appropriate kind of glass in order to do it so that you don't have a back reflected beam. And I've just discovered there's a plate glass that does it, and it has a 50-50 reflectance supposedly, and it only reflects one beam. It doesn't reflect off the back surface. Well, we'll see. Okay, let's talk about dichroic. Dichroic means that it helps to pass wavelengths only in one frequency. So if you got red, green, and blue, it might pass the red, but it's not going to pass the green and blue. It's not going to pass all the colors on an equal basis. So the plate glass beam splitter that I'm looking at, I don't believe it's dichroic. It's just a plain piece of a special type of a glass that is a beam splitter that splits beams equally across the entire wavelength band. Well, the advertisement says the visible spectrum. Now, the visible spectrum is like 300 to 700 nanometers, okay? And so I want 220, 200 nanometers up to 1700 or 2200 or whatever up into the ultraviolet. Oh, wait a minute. The shorter wavelength is going to be maybe those higher wavelengths are the infrared because that's a larger wavelength. The larger wavelength is your infrared, which I don't care about. I'm more interested in the shorter wavelengths, which is ultraviolet. But anyway, let's listen to what I just want to explain that. Okay, so yeah, so this reflectance, it's reflecting a higher wavelength versus this is for like microscope stuff. Uh, Whatever, it's like it's not reflecting the 532 equally. It's changing the wavelength on the reflectance side, which is, I don't need that. I just need equal across all wavelengths. Oh my God. Holy God. What the holy hell? That's what I have in my basement. I just want to throw it in there. Yep. I got a I got a multi-million-dollar optics lab down in the basement and a furnace that doesn't work right now. So it's collecting moisture. Yeah, that's an optics lab. So what I wanted to mention is that the lenses is something I noticed about lenses. So when you look at the lens, every lens also has a reflectance, not just mirrors. So you look at a lens, and when you look at the reflectance of the signal, not you can look through it, but when you look at the reflectance, there's two things when you look at it. There's the back section of the mirror. And I'm thinking now, so if it's a regular lens, the back section is going to be concave. It's going to make the picture bigger, depending on what kind of lens you got. But what I notice is that no matter what kind of lens I've got, when I flip the lens around, the reflectance shows a magnified image. And when I flip it around again, it shows a normal image. So I was thinking maybe my lenses need to have the largest reflected side on the side that I can see, because that's what I'm using in my tuning cavity. So I want the largest side on my side, and I took some measurements, and I could see I could I could I made some measurements on this tuning cavity that I'm building, and they both have the concave mirrors on on the inside. And I've discovered that I can connect another lens to the one on the left, and I can move that lens around and focus it. I don't have to have two lenses in my tuning cavity, which is freaking awesome. That's some shit setup there, huh? Holy, what has she got in here for videos? Listening to the quantum realm. That would be interesting. Well, we'll go back to that in a minute. Yeah, let's just do this here. Okay, I really don't care about that. He's actually looking at the lens, I think. Oh, wait. How did he do that? What's that wire? Is that like a heater wire or something? Now, how did. Oh, I see what he did. He took the wire. He just took the wire at the end to raise up the glass so that so what happens is when the glass breaks, it breaks going down the line, and so he's raising up that where he put the crack in it with that machine, that wire glass cutter. He put the wire in there in the slot, and then he pushed down and he snapped it off. Damn. Okay. The only thing I don't have is a glass cutter. I got some front surface mirrors that I pulled out of printers. That's why I was talking about that. Yeah, interesting jig. We don't want that. Okay, so that's what I was asking myself. I could rotate the crystal. He's actually rotating. I don't know what he's actually rotating. He's just saying he's rotating the laser. Oh, he's rotating the diode. Ah, okay. Now see, with an incandescent light bulb, you're just looking at light. But I'm also going to use, which was my next stream, is to work on my LEDs. And I wasn't aware of the polarization aspect of lights coming out of the LEDs, depending on how they're turned. Luckily I've got some polarization filters. But anyway, I don't even see anything. That's nice. Really? Glass ceramic cooktops? I'm not really sure what he's doing. He's building a. I don't know what he's doing actually. Diffraction limited, huh? Well, I'm just going to copy this link and get back to it at some other point in time. Because I want to get into this beam splitter stuff. There's a couple of. There's one video I think it talks about it. I don't know. That's the picture of it right there. Along with the stupid ass fucking music. Yep, that's what it is. But supposedly it doesn't have, like, I don't know, it's not like regular glass. It's built in such a way that it doesn't reflect the back portion. It's built a certain way. It's kind of narrow. What the hell program is he using? I don't know what. I don't know what the hell this person's doing here. This is just design crap. Well, that's what that ended up being. Optical combiners been Yada, yada, yada. Bidirectional augmentations. Oh, this is some crap with. I don't know what this crap is going on. Association for Computing Machinery. Okay, that's nice. Holy. Oh my god. That is sick. Wow. Okay, that's just effing crazy. Okay, because we're talking about. We're talking about. So that proves right there if we already have the technology to store data in glass, that's the Superman freaking story about him going in and looking at the crystals and finding all the information about his history in the crystal. But the problem is how you gonna how if some civilization were to come here and put their information in some kind of a crystal, how would you know where how would you know which crystals? If you could send data through a piece of quartz glass utilizing string theory, the string theory would send out photons that would be able to locate. Uh, if you could imprint information on a quartz crystal, then send the photons through the quartz crystal using but light is well, infrared will go through walls, but still it's a line of sight type of thing. I think you'd have to go into X-rays, and you'd have to go into particles that are higher up that can go through walls and travel long distances like cosmic rays and stuff. You'd have to, but then even then, how could you store information like that on a quartz crystal? They're just using this laser, which is, they said femto laser. Let me see here. Ultrafast laser emits optical pulses lasting just a few quadrillionths of a second. Wow. Because energy is focused in such short bursts, it achieves extreme precision without transferring heat to surrounding materials. Yada 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 yada. LASIK, that's that eye surgery. Well, they just replaced my whole cornea, but cataract surgery. The laser softens and breaks up the cataract before the surgeon ever enters the eye. This reduces the surgical time. Um, Laser relies on a process called photoionization rather than cutting it with heat, creating a rapidly expanding cloud of free electrons. No thermal damage, 3D image integration, yada 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 yada. Non medical uses. Ultrafast spectroscopy is a physics language to capture step motor same shots of rapid process chemical bonds, etc., etc., etc. Yeah. I mean, a photon is a photon. A light particle is a light particle. It has to go. It has to. Well, I suppose it could bounce around all over the place and then head out the window, but all my windows are covered up. I don't have no window. I got shades. I live in a dungeon, so I don't have no light pollution. Anyway, yeah, no shit. Yeah. That is crazy. That is shit, huh? Oh, that's pretty, huh? Wow. That is some that is some shit, huh? Ah! Yeah, Superman with the crystals. Okay, well, anyway, let me. Oops, I got a video that I wanted to watch there about JJ. Let me look up. Okay, LED as a because this is what I'm actually working on. So LEDs like these little bulbs here. Okay, oops, I don't know why the hell I just. This is an IR. Usually you get IR transmitters and receivers. That's the things that you have in your remote controls when you send the channel numbers and everything that come across the it sends data, it modulates or with modulates or it sends data across the light beam. um, so we could take we could take a remote and push the buttons on a remote, send the laser, the infrared, the IR data into my test setup once I get it built. And if we can successfully record and decode the data that's coming off the remote, I think that would be a start. I don't know if the remote has the receiver in it, so that tells me that all of those the broken VCRs, they have IR receivers in them. So I can find some IR receivers for nothing. I picked a whole bunch of stuff up for parts. Let's see what this says here, because there's some information I'm looking for, but we're not going to get to it just yet. Okay, what stupid ass freaking music again. I don't know what he's doing there. Including the simplest way to test an IR LED. A receiver. Okay, good. Let's see what he does here. Oh, he's just going to test the usually it's like 0.7 volts across the diode when it's forward biased or something. I forget which. So he's gonna test the resistance, I think, and that sends a voltage. Yeah, just split them wires apart. Oh my god. Oh my god, look at him wrap the wire around. Oh, the pain, Dr. Smith. We can already see a number. You don't have to wrap it around a million times. Oh my god, I'm having that poor diode. The black leg to the short leg, well, whatever. You can do it both ways. Yeah, what is this music on here? He doesn't even tell you what the hell is going on. Moron. Um, there's a little circuit. Let's check this one out here. Yeah, more fucking music again with people that don't know what the fuck they're doing. Alright, so here's one here. How to use a transmitter LED sensor as a receive sensor. Okay. Are you fucking kidding me with this fucking music? When they play this music, I don't even listen to it. I don't even watch it. Makes me sick. What's this one here? Pioneer receiver, LED upgrade. Use transmitter as a receiver. I don't know what the fucking hell he's doing there. Let's see here. More music? Yeah, let's listen to some more fucking music, right? Unravel mysteries for LED works. Repair LED light by replacing chips. Yada yada yada. How to check transmitter and receiver. Yada yada. It's not telling me. It's not giving me the information I want to know, which I already have, by the way. They're not going to tell me. It's not in here. Alright, let's do this. Okay, let's see what this guy's got to talk about here. Not quite what I'm looking for. The fuck? You know what? It's not even in here. I'll be damned. The fuck? Huh. I don't know what the fuck that is. It's not here. They don't even have it in here. That setup right there with the white, blue, and red LEDs is voltage levels, audio levels converted into the LED colors. Big ass deal. I will be damned. It's not here. It's almost like it was deleted because they don't want you to know how to do this. SOB. Huh. What's an LEP? That's just a collimated beam. Never heard of it. It's nice. What has this guy got on here? I don't know what an LEP is. Probably costs a lot of money. 2,000 lumens. Yeah, okay, whatever. Well, it's not there. So, we're just going to do this on my own. So, my next stream is going to be involving a bot that gets rid of these assholes that come into my stream and send these little signals here that say, we want you to visit this, and if you do, you can get more viewers. F off. Thank you. Have a nice day. So, back to the pyramid and back to some wonderful music to say goodnight to. Let's see. We can just get rid of that. Is my mic working? Yeah, it is. Oh, you know what's not working? The fuck? Oh, I didn't reset because... Oh, shit. You know what? Oh, my God in heaven. You know what? I don't believe any of the audio. Nope, none of the audio from all of that videos that I was doing came through because the setting was set up for my music stream last night. Oh, what joy! Well, you'll just have to figure that out, won't you? So anyway, I fixed that problem. Now we're gonna listen to some music while I jibber jabber for a minute and call it a night because that's what I'm gonna do. So, you've got a regular LED like the ones that I was showing you there, and but the ones that I was showing you are built specifically for transmitting, and another one's built for receiving. Well, it turns out that you can file the top of a regular LED and turn it into a receiver. So that's what I thought I was going to stream tonight, and for some reason, it doesn't look like I'm going there. But that's going to be my job for tomorrow because I've got to work on my voltage, my power supply setup. I got to be able to have a controlled voltage power supply, which I don't typically have. So I got to do that. My tuning cavity, for all intents and purposes, is done, except for the one lens on the right hand side. I've got to build an adapter for that so I can move it back and forth. And then I set that entire tuning cavity inside my interferometer. And then I'm not using front surface mirrors. I'm using just crap mirrors, and then maybe I can do something with those front surface mirrors. And those things are thick. I mean, they're like half an inch, quarter of an inch thick. I don't know how I'm gonna break them. Unless if I just get mad and snap them in half. You could do the wire thing, I think. That's what I'm going to do, because I got to do So you score the thing. I don't have a glass cutter. I think I need one. I had one. I don't know where that glass cutter is. I have no idea. It was a blue one, come to think of it. They don't cost that much. Maybe I could get one off of Amazon. Because I gotta go there anyway, huh? Let me see here. What is this crap here? I was also looking at that, but I wonder where's the other one. That one's $17. I was looking at a camera lens, and it's actually it's a pinhole lens, and it's only 0.25 millimeters, which is like absolutely freaking gorgeous, right? Maybe it'll work. And so that would be cool. I don't know if I think I only need one of them, and that pinhole goes into the place of the whatchamacallit thing, the little knife edge splitter thingy. So there's that one. We don't want this one, so I'm going to look up glass cutter. And the reason for the glass cutter is to cut that mirror. And then once I get it scored, then I can take hot wire at a very high temperature and heat it, and then put it in ice cold water, and then heat it again, put it in ice cold water, and go back and forth until it finally melts through. Oh, they got 4-inch tile cutter, diamond saw blades for angle grinder. That's a glass cutter. That's a tile cutter. Jigsaw. 4-inch diamond jigsaw blade, $30. I don't think so. Yeah, it's only $2.50. Oh, I know what that is. That's a different sized loops that they put on this handle, and you can score the glass. It goes around in a circle. Oh, that's kind of interesting. Replacement compass glass, circular guide cutter head, yada yada. glass cutter kit, carbide tile cutting tool, portable mirror screwing tool with replacement blades, screwdriver, oil feeder, an oil feeder. Oh, they had another. Okay. What's this one here? Glass cutter kit carbide with an oil feeder. It's only $3.60. Stained glass tiles, mirror, mosaic, 5-piece set, cutting range with 2 sizes of blade, 6 to 12 millimeter. Glass set for cutting different thicknesses of glass. It is 80 chains of bait according to your whatever. It's good enough to me. 9-piece glass cutting tool set. Oh, that's that thing that goes around in a circle to make circular glass cuts, which I don't need. That's $12. Two to 20 millimeter glass cutter head. This is 6 to 12, 12 to 20. This is 2 to 20 millimeter. This one is $8.97. The other one is $3.60. Why would I need one that's so large? Two to 6, 6 to 12, and 12 to 20. 3 replacement cutting heads. Why does it say 12 to 20? What does that mean? 12 to 20 millimeter. I don't know what that means. A must for cutting thick glass, heat treated for enhanced wear resistance. This is 6 to 12, 12 to 20, 2 sizes of blades, whatever the heck that means. Okay, I'm gonna grab this one here. What's this one here? An extension bar. Oh, I don't need the extension bar. I'm not doing circle crap. Alright, so I'm gonna add that to my cart. To my cart. Then I want to add I hope I got it here. What the fuck is it? Oh shit. Okay, that one right there. I'm going to add this to the cart, and that's going to be oh my fucking god. Are you fucking kidding me? Wait a minute, let's go back here. Okay, I refreshed the page. So when you look at stuff on Amazon, they put this code back because they want you to do all kinds of fucking referrals and shit like that. So you just get rid of all that extra code and put the item on there and you're good to go. Now where's my shit though? Let's go over here, go to my cart. What the fuck? That's not my cart. I got 9 items on my cart. Why is this Amazon so fucking slow? Oh, I put the diffraction grading thing on there. I gotta look that up because I found some diffraction grading paper. This is 1 foot by 6 inches. It's $15. Canine crystal blank for inner laser engraving. I don't know how to do that. I just put that there for a reference, didn't I? The fuck? 9 items, 3, 4, 5, 6, and 8. Oh no, this should be minus. Crystal blank blocks for engraving. See, I've got a setup. What size is that? 2.3 inch crystal ball. 2.125 inches. That would just barely fit in that section there. I don't know how you actually do, let me stop this music for a minute because I think what I'm going to do is inner laser engraving. Let's take a look at that. Why not? Photons across the land. We're gonna look at some engraving stuff and see if that's something I can incorporate into my setup. It's a way to make money, you know, instead of just doing something. What is subsurface laser engraving or bubblegram technology as explained? Engraving inside glass, the game-changing Omni X UV laser. Let's check this one out right here.
Okay, so check this
sound
because
now.
It's actually pretty amazing and it's really easy to do. This image isn't on the glass. This image is inside the glass. I created it with this new Omni X 5-watt UV laser that can do pretty much anything any other UV laser can do, but it can also engrave 3D designs inside solid glass. If you're a maker or a small business owner, this isn't just cool, this is like an entirely new product line. I'm going to show you in this video how it works and why it might become the most versatile laser in your workshop. So let's get to it. So Commarker's first UV laser, the Omni 1, is a compact workhorse. It's great for quick marks on plastic, leather, most metals, and pretty much any other material, but now it has a sibling. By comparison, this new Omni X feels like a serious upgrade, not just a tweak of the Omni 1. For starters, you get a full enclosed chassis, which is a big win for safety and controlling dust and fumes. Inside that cabinet, there's a 5-watt UV laser, but it's now paired with an accurate autofocus and a powered Z-axis, and that opens the door for more advanced work like 3D engraving inside solid glass. Around back, there's a full set of connectors, so you can have a foot pedal, rotary tool, interior lighting, and there's even a port for an extension table, which is going to expand the workspace by over 266% for larger jobs, and I'll show you that in a minute. In short, the Omni X has the same core power as its predecessor, but it's way more capable and way more refined. If the Omni 1 was your first intro to UV lasers, then the X is going to feel like the version that was made for serious projects and real business use. So now let's talk about software. And one of the first questions I get asked with any laser
Extra
is, does
credit.
it work with Lightburn? And of course, the short answer here is yes. Now, the Omni X uses a different laser module than the Omni 1, and that means rather than pick the JPT device in Lightburn, you're going to instead pick the BSL laser device. Now, at the time I'm creating this, there isn't a calibration file provided by CommMarker, so I had to basically do a manual calibration. It's not that big a deal, and I'll put a link up in the corner here to a video I did on galvo calibration. It's pretty simple. After you get all this set up, the laser basically works like any other laser, and if you're already comfortable in Lightburn, then you're going to feel right at home with basic engraving jobs. What you won't be able to do in Lightburn is take advantage of all of the 3D capabilities of the Omni X, and for that, we have a different tool. And that new tool is called CommMarker Studio, and it's a Lightburn kind of equivalent. It's not quite as powerful, but it's also not quite as complex. So when I turn the laser on, it will just automatically connect. I don't have to do anything fancy. I can then do something like drop an image in. In this case, it's a black and white image.
How does it
Although I
make a
can adjust the
3D though?
contrast and brightness, it doesn't make a lot of sense here. And I can scale, of course. I can position. Then let's say I wanted to drop some text on this. I can just plunk it down there. Again, it's a lot like Lightburn from that regard. I can go edit the text, and I'll call this guy Doctor Who, and I'll confirm it. And once I do that, then I can certainly select both of these things and position them relative to each other, so I can do basic alignment. I can then go over to the right hand side, and you'll see two layers there, and one of them is that text. I can say fill it. Once I'm happy with my image, I can then go pick the material that I want, and in this case I'll just say let's use cork, and it will go and automatically set those values. Now those values come from their material library, but you can completely customize this if you want. And you can go change some values here. If you decide you don't like the default settings, you can go change them. Now, after that, you can do things like focus. And when I do the focus here, I'll drop a piece of material down and hit the autofocus.
That is cork.
And you'll see the focus actually come down to where it's supposed to be. And when I'm happy with that, I can just confirm it. Then I can do an outline, like a preview. And I'll need a card for this of some sort because it uses the UV laser for framing. And again, once I'm happy with all of that, I can just hit the start and I can go and engrave a job. And in this case, I didn't pay a whole lot of attention to alignment here, but you can see that it came out and it looks really nice. So suffice it to say that a UV laser can engrave on almost any surface. So I didn't do an exhaustive set of engravings here, but I did quite a few.
5-watt UV laser.
If you want to see even more, then check out my original Omni 1 review. I'll put a link up in the corner here. And that'll give you a more ITC cards, both silver, and I also did some black ones. And you can go as high as you want. It takes a long time. And this block up one at a souvenir shop, and then the frequency is 30. And I'll show you the sped up version of this. This actually took quite a bit of time. It took about an hour, but the results are spectacular here. You can see
3D,
complete 3D
wood.
effect, and I think that's really just amazing. So next I'll look at full
nice.
3D engraving inside a block of glass, and this is my most favorite feature of the Omni X, specifically because this technique has been around for a very long time, but the lasers to do it typically had previously cost $40,000-$50,000, which is why when you bought these engraved blocks at a souvenir shop, they're very popular for souvenirs. They always cost like upwards of $100. Well, now anyone who's got a budget and a side hustle or a small business can do this right in your own shop, and I think that's the coolest thing ever. So let's get to it, and I'm gonna go and select the 3D glass mode, and again I'll pick a file. Now I loaded a couple of STL files from Thingiverse, in this case Starship Enterprise, the original, And you can see the yellow outline there.
Let's see
That's
if
the
it's
actual
on
shape of the block, and
Amazon.
you can change it on the upper right side. So I'll rotate the object vertically here because I'm going to stand this block up when I'm doing the engraving, and then I'm going to scale it down to the size of so it fits inside the box. And so I zoomed it down to 0.6. I'm actually going to go to 0.5 just to make it fit really nicely, nice proportions. You don't really have to do anything with the settings here because they're all pre-configured for glass. Really, all you have to do is hit the start button and watch it go. And this is,
Radar.
again, this is cool. This is the sped up version. This took about 20 minutes, so it's actually really quick too. And when you're done, the
Wow.
result is just amazing. And you can see the level of detail here is pretty incredible.
That's
And they're
pretty
fully 3D,
pretty
which means
sick, huh?
anyone who sees them is like super excited. So if you're doing work with another business, you have an opportunity to sell these as maybe paperweights with their company logo in them. Tell them to take them to trade shows. They're a pretty expensive giveaway, but you can do that. I've seen these given away at trade shows. The other thing you can do is if you have access to maybe a souvenir shop, engrave a local attraction in these things in 3D, and
There's
they
a
will buy
press
these
the
things and
people
sell
at the
them. They'll sell
malls. They
tons of
sell
these.
this stuff.
So you can do that. Now, there's one other approach you can take here. You can also do flat images, but engrave them into things that are more appropriate for awards of recognition. And you can buy these on Amazon. You can actually put photos in these things too, which is kind of cool. But if you want to do awards, thinking for another business, you can basically buy these things. You pick your flat image, focus on the surface, and then drop it by however half the thickness of your material, basically. And then you can do these engravings, and you can see these things. They're flat, but they're embedded in the glass, and they they just look very appealing, and people will love these things if they're.
Yeah, I know. That's nice. So he said something to the effect of, what's a 12 watt? About this item, autofocus with LiDAR ranging system. LiDAR ranging to get the 3D. It goes up 150 to 400 millimeter working area, yada yada yada. UV laser, yada yada yada. Com marker, yada yada. 110 volt. Yeah, wavelength is 355 nanometers at 12 watts. I don't use high powered lasers for anything. Oh, it says 1.95 milliwatts, but it's UV. Yeah, whatever, you know? So, that's the story. I am done for the night. I don't think it's too late for me to work on any electronic stuff, but I am going to get it. It is kind of set up, and so actually, what I could do, actually, well, my lasers that my LEDs that I cut off the top are drying out because I had to clean them. So tomorrow it's going to be LEDs, my power supply, um, well, there's something that I did want to look at though. I wonder if I can find it in here. Maybe we can just look this up real quick. Uh, let's just go ahead and I'll bring this back up because this is sort of interesting. I watched the video. Yeah, it's this one right here. This is
Clint Eastwood?
That's not my last name.
To me earlier.
so as it happens. So he's using Fresnel lenses, which I don't have. You can use Fresnel lenses to start fires, literally. These are amateur radio operators, of which I am one, And there looks like they're using a bunch of lasers into some Fresnel lenses, and they're bouncing it off the atmosphere and going to another receiver. And they're actually communicating. Oh, there's cloud bounce optical communications.
And it didn't catch.
Okay, well, watt LEDs have successfully spanned 173 miles across the Utah desert with two-way voice communications.
That's awesome.
Right, yeah. And that was with, these are 10 times as powerful, but we'll be only going a few hundred meters tonight. Mm-hmm. And since we aren't on the mountain, we will do something silly like point at that flagpole over there or the antenna pole and bounce the light off of that and have another radio over there, and we'll be able to talk to each other without line of sight, direct line of sight. Normally you would do line of sight, but we can't do that.
So you're transmitting voice over it?
Voice, yes.
And you got two boxes. One is the transmitter and one is the receiver?
Well, one half is the transmitter, the other half is the receiver. These are both transceiver-capable boxes. Mm-hmm. And they're actually full duplex, because when you shoot the beam out, unless there's a lot of dust, the receiver and the transmitter can't hear each other. So we have done many QSOs where we're just standing around talking to each other, even though we might be 100 miles apart or something like that.
Oh, that's pretty cool. Mm-hmm. So is it the glass or is that a focusing lens?
These use Fresnel lenses, which are essentially, you take the curved part of the lens and you slice it away because you only need the parts that change. Mm-hmm. And we use those because they are cheap and flat and light, especially since this had to be, when we did the 173 mile stuff, this was carried on the back of another ham who's behind the camera to the top of a mountain in the dark. I had this one in my car. I drove up there, but to the other mountain in northern Utah. But these are good enough for LEDs, which are not coherent, and which is an advantage since you don't have the coherency breaking up and causing flickering or scintillation. And LEDs are immune to that for the most part. And since they're not lasers, you can use inaccurate but good enough lenses to collimate a beam so the energy goes straight rather than spreads everywhere. So these, the effective radiated power of these is tens of kilowatts, if you were to think of antenna terms. A few watts of light in, tens of kilowatts effective rated power because of the gain of the lenses, because they're not spread out.
That's pretty cool. And where can we go to find out more information about this project?
The website modulatedlight.org.
I don't know if I'd want to stand in front of that.
Thank you very much for taking the time. I appreciate it.
Okay, K7RJ, K7RJ, K7OEI, Delta November 23.
K7OEI, K7RJ, DN
Is that the received light bouncing off that flagpole?
Delta November 23, over.
Copy your Delta
Look at the
November
light
23.
showing up on that flagpole.
Yeah, so we'll do the feedback. There we go. I'm on 550 terahertz, and I think you're on 472.
Roger. Two widely spaced frequencies all in the same band.
Well, I'm still running push to talk, of course, because you see green. But I don't know what the SWR this transmitter is, but I'm seeing a lot of reflected power off the cactus. Let's see. Saguaro QSO, I guess that's what it is. I wonder if that could be a thing, you know. Worked all Saguaros, WAS.
Thank you to all my Patreon supporters. You can support me on Patreon.
Was that the same dude? W1VLF, that's somebody else.
VLF, and what you've just been listening to was the sound of a modulated light beam that was bounced off a cloud and received approximately 5 miles away. I got this idea.
So you're not supposed to use lasers into the clouds unless you can't see them, like if it's a non-visual, because I don't think non-visual laser light would affect any avionics equipment. They're just talking about the visual lasers, which would blind pilots, which is illegal.
From a searchlight that I noticed you could see from miles away, and thought, well, if a searchlight can be visible from that kind of distance in a big radius, why can't my own light beam be that way? And I can modulate it and receive it. I'm doing an experiment here. This is a very short video, which is just going to capture the highlights. And if somebody's interested, they can go back and or leave a comment down below. And that way there, I'll know that there is enough interest and I'll make a full video of it. Just a couple of quick parameters. The transmitter that I made was 816 LEDs removed from remote controls when I worked in the cable television industry, all in parallel, series parallel complement. And the cloud height that evening was 10,000 feet.
He's got
And
some
the distance
coolers on
between
the LEDs.
the two sites was approximately
That's a
5
shit ton
miles
of
round trip
LEDs.
from
How
the
many
ground
did
to
he
the
say?
cloud, land and back to ground. From 116 made was 816 LEDs. From the points on the Earth, it was only about 3.5 miles. But those points were on opposite sides of a mountain. At the end of this, you'll hear there are two complete audio files. Each one of them contains about 20 seconds worth of just a tone and then some CW. The first one will be unfiltered, and you might be able to hear the signal buried in there. And the second one is filtered, and I used a product called Cool Edit, which was a popular audio
Yep.
program,
I got that program.
editing and filtering program. So again, if this is something that interests you, I have a lot more information. I did a presentation once at a ham radio club about this. Leave a comment down below, and
doesn't tell
if
you
there's
what the
enough interest,
frequency of the
I'll
light
spend the
beam
time,
is.
pull that out, and we'll go through it in a little more detail. Thanks a lot. I appreciate you guys listening to this. And
Well, it would
if
be
you're
IR
interested,
because,
please subscribe
remote
and go
controls
back and look
use
at some of my
IR,
former
which
videos.
is
There's quite a
infrared.
few interesting and maybe eclectic kinds of things there.
Oh,
Anyway,
shit.
73 from the computer voiceover network here at W1VLF.
Oh, I can hear the tone. It's Morse code. He's calling CQ. 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 W1 VLF. CQ from W1 VLF. Now let's see what it sounds like when it's filtered. That's not, so the only problem there, it's not real-time filtering, it's a recording. Oh, that's the Morse code. It's like there's like feedback in there. So you can use you could run this into Ableton as a live loop, because that's why I've been doing all my music, learning how to do live looping and stuff. There's there's programs that you can use in Ableton as fuck, I don't even know what you call the damn things. VSTs. You put the VSTs in there, and we can do this filtering on a live basis. I don't know how else you would do it, because the other ones, I'm not sure if he says Cool Edit, and I don't know if that's a live audio filtering or not, but listen. That's CQ. CQ. W1 VLF. W1 VLF. What's this one here?
Hey everybody, my name is
994 nanometers. That's a higher number.
to the lab. Haven't made a video in quite some time.
Let's see something here. Yeah, see if you look at this picture, the larger numbers are down towards the infrared. The longer wavelengths are infrared? I thought it was the other way around. Infrared and UV. UV goes up. UV is... Fuck. I can't see that fucking bullshit in there. This is the best one right here. He said 900 and something. Oh yeah, okay, 700. So that's in the infrared spectrum. That's heat though. Oh, so if you use infrared at night, that would work really good because at nighttime it's cold. And a focused infrared beam makes a lot of sense. But why that frequency instead of UV?
And I thought this one might be of interest to a lot of different people because I've been getting questions on some of the short. It's not good. So at your own risk. Beam angles will. Like the 10 gigahertz guys and microwave guys or anyone, you wouldn't stick your eyeball down the a waveguide with 10 watts of RF in it. Just like you wouldn't sit and stare at the large array I showed you before.
Right. We know that.
It's a 6-degree beam width, so the light spreads pretty quickly. But we're going to talk about that in the next scene here. But just use common sense, right? Don't stand in front of the thing for half an hour looking into it, trying to say, "Hey, can I see it? Can I see it?" No, it's not good. So at your own risk. Beam ceiling height was 10,000 feet. And if you did the math, you came up with, I forget what the angle was that he needed to point at and I needed to point at, call it 5 milliwatts or 10 milliwatts or 100 or a watt, whatever it is. It has only spread to the diameter of 1 foot at 1,000 feet. That's still potentially, depending on the laser power over here, and the fact that we're dealing with light waves that don't make us blink because we can't see them, so there's no blink response. Those are, that's still, in my opinion, dangerous. Whereas the 6-degree beam width of the LED array is now, that amount of power is scattered into a 100-foot diameter. So the power density is relatively low here at 100 feet. So that's one reason why I don't use lasers, is they're dangerous up close. We don't blink on 940 nanometers. And also, you buy a laser, on eBay, it typically comes from China. It says 5 milliwatts eye safe, but you really have no idea of what kind of power is coming out of there. Just not worth it. I have a couple of cameras that see infrared with spots burned into them, into the CCD device.
Well, yeah.
And that was because the laser passed by it. So I have not worked with lasers for this kind of communication system in quite a while.
That's interesting too, because I'm putting a camera at the end of. Well, no, I'm not using lasers. I'm not. Well, there is a laser that goes through the system to tune it, but I'm wanting to use an LED with a pinhole and a collimated beam because I'm going to simulate the full spectrum going through the system, which is, whatever the hell, it's not a laser.
So people are going to say, well, that's a lot of infrared energy, from those 140 diodes. And so Fred came up with this idea, and I built one of these. And, okay, so if you look on the right side first, up here, 6 feet from my high power array of 940, that probably should, I have several 940 arrays, that should probably be 6 degrees. But 6 feet away from that high powered array, we have a half scale in microamps, right? 50 microamps. The detector is up here. Can't see it in this picture. Okay. On an overcast day, when you stand outside, that meter is pinned, so I have no idea how much more it is. So at 6 feet away from this high power array, you're already at half of what you're exposed to at 940 nanometers outside. And by the way, this is the detector up here. So essentially it's just a little solar panel with a bandpass filter in front of it, one that restricts most of the visible light and only allows the infrared light to pass through. So what happened? Okay. So you're saying, well, I have 140 of these LEDs. How far before they actually combine into a single beam? And you take 6 degrees. Let's see. Let's see. I forgot how far. I guess I forgot to put the distance in between these two. So, but anyway, you can look at, here's one LED and here's another LED. And at some point, those two cones are going to overlap, right? So if you take those same two LEDs and you say, oh, they're 1 inch apart, those two cones are going to coincide at 8 inches. The reality is those LEDs are 0.375 inches away, and they're already half, 50% coaxial, if you want to say that, at 8 inches. So once you move out further and further, they form one beam. It's sort of like looking at I don't know, headlights or some multi illuminator, multi-source illuminator from a great distance. It appears that's setting the resolution though, because you should be able to read all. And they were in a box and they were air pressurized. Is a maybe 10 ohm resistor. I don't have this array anymore. It's long gone. But again, removing these 800 and something LEDs, I think my wife thought I was nuts. Well, I was nuts. I'll have to agree with her on that. But that's just a closer look, okay? So let's say this side of the array goes to ground, and this side of the array goes to a 10 ohm resistor in series with the switching voltage that's setting the tone that's on these, okay? And they were in a box, and they were air pressurized. I forget how many amps this drew at 12 volts, but it was considerable. But the power density was very, very low by today's standards. And you could see this. I took these pictures with something called a Snappy, if anybody remembers. It's just noise. Absolute just noise. Validate the system that you're using. But here is the response of a typical photodiode. And they vary slightly, right? Some have a little more enhancement here, some go up a little higher, but we're operating at 940, right here at the knee. So why am I showing you this? Because at 940 nanometers, that's your interest right here. That's what I want to see. That's what my lens, my optical system wants to see. All this other crap, and look at the amplitude here, is just noise. Absolute just noise. Even up, and in fact, there's noise on 940 nanometers, which you can't get rid of unless the sun goes away, which happens at night. But this is all noise. So how do you get rid of this? Well, you go to an optical filter. So here's that 940 nanometers, and you can see that percentage-wise, it's down significantly at 900 and at 960. Whoop, backwards. Let me go back. So you're just taking a slice out of this, just like you'd put.
Let me just look something up really quickly here. I'm looking up optical filter on Amazon. Not that I need them because I can make my own, but I'm just curious. I've got filters too. I got a bunch of filters that I bought from my telescope, which I'm going to be using, and I can test those and find out what. Yeah, these are. Star lens filters, 6-color optical glass filter set for telescopes. I've got a couple of those. Diving lens filter for underwater. Diving lens, I don't need any of that. 8-point starburst lens filter. What does that do? Well, it just does twinkles. It adds twinkles. We don't need to add noise into our pictures for sure. Yeah, that's the red, green, and blue, and the other ones. These are like $7 a piece. Holy shit. The whole set's like $24 or something. And that's 26. No. Cart subtotal. That's not my cart subtotal. Only 16 left. Let me look at this thing here. Just bear with me for a minute. I'm wondering about, oh, that's the cheapest one they've got. It is. It's the cheapest one they got. 6-pack square crystal display bases. A prism cube. Crystal domes. I don't care about that RGB crap. Bear with me, I'm just looking at some stuff here. That's a blank. Don't know what size that is. Holy shit. Two inches. crystal resin acrylic. .5 inch, but that has a color to it. It's a green one. And there's a cylinder. You know, that's just too much. I'll have to deal with that. That's it, I guess. What's this here? Sorry, I'm kind of doing something here. I'll be right with you in a moment here to finish what I'm doing. Single set printer. What is this? Oh, I've discovered something. Oh shit, they don't have it either. It's 1,500, 1,000, 13,000. Yada 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 yada. This diffraction gradient covers a wavelength range from 200 to 2,000, etc. Precise measurement designed with 50, 100, transfer green loss for yada yada. Yeah, I don't care about that. But this is interesting. Single slit, double slits, Poisson spot, Moire pattern optical elements. Single slit, combination, double slits, Moire, Poisson, round holes, $10. That's cheaper than that other thing, and that's a slide. .2. Those are awful close together. I don't care about that. I don't know what that is. Hmm. Hmm. .05, .1.2. This one is .2, .3, .4. You know what? What is this one though? Well, it doesn't say. Hmm. Interesting. I need this. So what I don't need is that other item. I'm going to get rid of this. That helps a little. So I got some slits that are down to 0.2, 0.1, and 0.005. I think that's pretty good. And everything is available. Whoops, let's see. Only 16 left in stock. Only 10 left in stock. Okay, I'll just go back to what I was doing.
Put a bandpass filter up ahead of your HF rig or whatever. You need to have an optical filter. At least during the day. At night, there's not enough, I don't think, IR away from my house. And here's 3 examples pointing north at the weak signal source. And my sons are texting me. I'm going to put this thing on quiet so I don't... Guys, don't you know I'm making a video? There we go. Okay, so the only thing that has changed is that we went from day to night. Okay, so if you look at this signal level here, the noise floor is minus 90 because of the sunlight. And this is, again, I'm pointed north, so I'm not looking at the sun. Oh, by the way, never point your optical receiver at the sun. You could say goodbye to your photo detector and probably half of the other components in there if the full sunlight falls on it. There's a funny story about that. I'll tell you a little bit later. But here's my weak signal source. Okay, look at the signal. Minus 80, minus 80, minus 75. So not a huge difference. But look at the noise floor. Minus 90 during the day. It's noon and it's overcast, so I got a little bit better signal to noise. It's minus 100, so now the signal noise ratio is 20 dB. And this is the dark sky at night pointing. The noise floor drops to 120, and so now you're at 25 plus 20 is a 40 dB signal to noise ratio. And this is what it looks like in the waterfall. The reason why you're seeing 2 carriers here is because this was a Q65 digital mode experimental weak signal source I was messing around with. But it's really, really dramatic. Okay, so you go from a signal to noise ratio of 10 to a signal to noise ratio of
it looks good on that left-hand screen, though.
Very, very dramatic. And so you need to, optimize your system to try to get rid of every
when
piece
I'm
of
starting
noise
out, man, everything is going to be
because
reflecting
you're
off of everywhere.
Fighting against the sun, which is the ultimate noise source, I guess. So optical detectors, there's no lack of optical detectors. I personally use this one. It's the Pt24 PI infrared optical detector. It's an optical detector. It's a little solar panel. It's a solar panel that's like this is encapsulated. The solar panel's in here. This is actually the back side of it. You wouldn't use that side. You'd use the other side, which is flat. But inside here, about 4 millimeters by 4 millimeters is the active area. The rest of this stuff is just for convenience and because these were through-hole parts. I don't know how they were placed, but anyhow, you need an amplifier after this. So that's where this TIA or trans impedance amplifier comes in. This black surface here, this epoxy, this encapsulated epoxy, is a bandpass filter, but it's a very broad, not like a third little module, unless you find them used on eBay. These things were like $50, but it was complete receiver, all built in. But the problem is don't even think about using these during the day. They're just even with double bandpass filters in front of the detector, they're incredibly noisy.
Oh, that's interesting.
So anyway,
I think I have the Opta 101. I think I ordered some of those. It's interesting that he says that they're noisy. So that's a challenge to build a circuit to find out what the noise floor is of the circuit itself. Type of thing. That's what I got to do. I got to build some stuff.
It's just a little bit more about detectors. What do we got? Okay, so here's a really good example of why does size matter, right? Okay, in my weak signal source, don't know if you can see it or not, but you see where my mouse is? There's a tiny little white box there. Okay, that's the weak signal source. And the diode is infinitely smaller.
I like his New York accent.
So, what's this? Oh, this opening is about 10 by 10. It's less, but let's call it 10 by 10, just so that we can have, just for the topic, the conversation here. It's 20 kilohertz. It might be 18 or 19 or 20 or 21, but for this purpose, it's experimenting. It works out really great. So what comes out of here? A square wave comes out of here. Here's the square wave, and that square wave to some extent is a function of the voltage input. If you put 30 volts in, which they say you can, you're not going to get 30 volts out of here of PWM signal, and it's not going to blow up your diode. There's a current limiting resistor in there. But so power goes in. I ran them off 9 volts. The LED ran off of the 9 volts, but there wasn't 9 volts across the LED. But so now you have, what do you have? You have the baseline, you have 0 volts, then you have a plus voltage, and that for a period, then you have 0 volts, a plus voltage, a 0 volts, a plus voltage, and this is happening at your choice of frequency. I happen to use, I think, 16, 17 kilohertz because I'm using an SDR for detection, and I don't like going down below 10 kilohertz. Fred and the guys like to use 600 hertz because they're listening by ear. That has advantages.
I got 2 SDRs,
of
which
a very
I got to get
simplistic
into.
receive system without the use of a computer. But if you go up to 16 or 18 or 20 or 30 kilohertz, then you can use an SDR with filtering, with all sorts of different detection modes and so on. So anyway, that could be a transmitter. Let's move on. Here's a transmitter right here. This thing, let's say we set it for 500 hertz, right? We go back, we set this signal for output for 500 hertz, 50% duty cycle, and you take that chain that coming out, and you literally connect it right to a diode. Now you have a weak signal source. It may not be as weak as you want, but you have a weak signal source. And in fact, you have a transmitter. You insert a key where the arrow is, and you have a CW transmitter. When you key the transmitter, you connect this connection to here, and what happens is the LED, sends out a pulse, a dot or a dash of say 500 hertz, like we talked about before. So building something like this can be incredibly cheap and fulfilling. I mean, my weak signal source is many times weaker than this thing. And when you get to that point in your receivers, you need something like that to optimize focal points and all the rest of this stuff. But anyway, that's a basic is Vishay. Boy, and I got it wrong here too. That's supposed to be 940 watts times 1, 2, 3, 4, 5. Visual light that we're not interested in at all, and you put a bigger antenna on it. What do you mean? Controllers were like $4, and the IRL 540 logic level FET was another $3 or $4. This is the array you saw in the beginning of the video, and it's I wish I had those numbers down somewhere. I'm notorious once you get a more complex receiver system like this. This is my purely because my choice This is how I like to do it. Pause this for a second because that audio, my audio is very, very low. But this is the 140 LED array right here. And this is the one single LED. One of those 5940 LEDs, 45 cents.
45
And
cents.
the reason I did this was because at 4 miles, it wasn't nighttime, but it was 4 miles away. It was 4 or 5 o'clock in the afternoon, so the sun was nowhere near at its peak, and I wasn't sure I was going to be able to hear one LED at 4 miles. So I put the big transmitter up there and the little single LED transmitter up there, and you'll see that there is plenty of headroom. And this isn't even at night. This is I don't know, 4 in the
That's a
afternoon, 5 in
CQ.
the afternoon here with the daylight. I'm gonna blast right with the photodiode, and then the one on the end here.
Okay, that's enough of that. Let me just go to his videos and see what he's got in here. So he did optical communications update 2. That was 8 months ago. Laser experiments, yada yada yada. Sun noise mitigation for daytime optical. Sun noise mitigation, that's interesting. 2 miles optical path with 1 LED. Okay, I can go with that. Improvement to optical. These are, so this is IR, infrared receiver and transmitter. 2 miles on just one. Let's see here. What is this here? Just out of curiosity. Russian pirate radio stations on satellites. Yada yada. Selective. I don't know if he goes into SDR stuff or not. Oh, there's a comb generator. Poor man's comb generator. Check that out. SDR spectrum analyzer. Decoding FM multiplex. SDR uno, yada. Uno, dos, tres. Holy shit. Are you fucking kidding me? That's his tower? Look at that thing wobble. He must have a one of those flying things, those drones, go up there to look at it. Way up there. That's a moon bounce antenna. That's what that is.
Null it out. So if we look here, so let's take a look at this trans impedance amplifier, because this is a slightly different arrangement than what Fred and Renee and those guys are using. I'm using a discrete LED, photodiode, and this trans impedance amplifier. And here's a closer look at that. Okay. The output. Wow, that's weird. Oh, okay. Something's going on in the camera here. This is the output. It's a N connect. SMA goes over to my little AirSpy receiver here, and the input is typically an SMA here, but I've taken the SMA off so that I can get a much shorter connection to the photodiode. Okay, and I'll try to show you this. I'm not sure you'll be able to see it really well. Maybe I'll snap some close-up pictures of this, but
Trans impedance amplifier. Why the hell would you need that on a photodiode?
the detector sits inside this box, inside this little box, forcing the photo detector into saturation. Okay, so here's a quick demo. The DC that's coming through here. We've also filtered, so we're only looking at a very narrow spectrum, maybe 10 nanometers. But somehow that's still not working very well. and it's because the sun is forcing the photo detector into. So my detector size is roughly the same size as that square. So what does that tell you? That tells you that there's a ton of light falling on the detector from that 8 foot by 8 foot opening. But the only thing we want from that 8 foot by 8 foot opening is that tiny little LED. So we have a lot of noise falling on the detector. And when I say noise, I mean sun. You know what? I better check and see if we can actually see this okay. This is the background noise. All right. Now, we're back again. And if you look, we have 42 dB signal to noise ratio. All right. And I'm going to apply some bias now. And here's where I applied the bias right here on this wire. I'm going to put some bias on it. Okay, that's a very small voltage right now. And then I have a pot. It's a 100K pot across 1.5 volt battery. So what I'm going to do is, well, let's take a look at what the signal to noise here is. It's now 47. Didn't make a hell of a lot of difference. It made a little, but not a lot. So let's turn up the bias. All right, so I'm forcing that diode that's making roughly, let's call it 0.5 volt from the sun, back down from the saturation point. And now we have a 56 dB signal to noise ratio.
Oh, that's interesting.
Okay, and you can actually see it here. It's significantly higher. Now, let's look at that signal to noise ratio, and I'm going to put too much bias on it, which means I'm now forcing the diode in well beyond the point where my bias equals the sunlight noise coming from the diode. And watch what happens to that signal to noise ratio. Okay, I'm going to increase it and then we'll walk over. Okay, and it's starting to drop off right now. It's down to 52. Here's a better way to look at it. We'll use the, okay, we went from minus 70, excuse me, from minus, whatever it was, 50 or so.
He's cut out a lot of the IR infrared,
so
though.
It's easier to see. I have more steps per division. All right, so we're running at about minus 68, 69, okay? And you can see it is doing. Now I'm going to go all the way down to no bias again, okay? And notice how the signal goes back into drops by significant amount. We're forcing that photodiode in and out of saturation. So I'm going to adjust it up. Okay, so there's some level of reverse bias on this diode. Pull it off. 67 to there, okay? Now you can look at this and you'll say, wow, propagation is changing, but not really. It's just the sun coming in and out from behind. Anyway, the reason why this doesn't cause any problem is because we've already taken the precaution of filtering the front end of this detector with a 940 nanometer, very narrow bandpass filter. And LEDs themselves, unless they're designed for it, don't put out any IR information, any IR.
So he's using a filter, plus he's doing bias on the diode to do something with the noise. Okay, so that's something new. Oh, shit. What was I thinking? I can't remember. Brain freeze.
Power. That's why I'm able to operate very well as an absolute from the noise floor. All right. Extremely sunny.
I'm hearing, speaking of noise. What's the next one here?
Hey everybody, this is Paul, W1VLF, and welcome back to the lab. And today we're going to step back a little bit from SDRs and go back to some of the fundamentals here. Now I'm going to tune the radio on the bottom here across the band as if I was tuning for another channel. Made a little spreadsheet to be able to show all the frequencies and the interference. Take a look at that on the SDR. We'll see if any of the things that we're talking about here are true, and the SDR will tell us whether they're true or not. So let's say you have and this is in the old days, right? The purely analog days, right? What do we have here? We have a mixer, which is going to take some signals in, two signals in, a local oscillator, and the RF amplifier. The RF. So you have an antenna, and in the case of the Grundig, it's sound converted by moving the parts. The local oscillator and the radio tuning the Grundig, the IF and the tuned frequency. This stuff all takes place in the AM, the FM band as well. It has some amplifiers associated with it, right? Here's the FM equivalent, right? The local oscillator is 10.7 above. Today we're going to talk about a super simple way to couple a receive loop like this into your SDR. Stick around. That will just couple the field into a radio such as this, whether you put it near it or in it, however. But the problem comes in when you spent your money on your SDR and there's no way to couple this in. Some of the commercial units, like this Grundig, have an extra loop that one or two turns that go around the perimeter, and they tap that off for you over here. But if you've built one of these other style loops and you want to couple it into your SDR, today we'll be using the HF Plus and Console 3. How do you do that? We talked about last time taking a loop like this that has a coupling output and attaching it directly to one of these things by driving this small ferrite. But we need to be able to extract energy from any one of these loops, and we're going to go over that today, and I'll show you what I've done, and we'll play a few games here and see what happens. Let me set up for that, and I'll be right back. Sweep through real quick so you can hear the, no wires, the conventional way of tuning this antenna.
But Donald Trump, for a couple of weeks or a month, talks about how Pennsylvania may have been compromised.
Okay, and as soon as I move it away. Okay, so what I have here is the loop that we're used to seeing, and a piece of coax cable connected to our HF Plus with a tiny little loop on it. This is about 1.5 inches in diameter. And as you could see, looking over at almost the entire broadcast band over there, there's not a lot of really big signals. So what I'm going to do is I'm going to allow this loop with the field that's around it to couple into this. And that's going to be our pickup. So you don't need to actually make physically modify this at all. And then we're going to try a couple other loops. Here's a little bit larger one, and here's a larger one. So there's a balance that you want to meet between how much signal you extract from this loop and how broad the response of the loop becomes. And in basic terms, the bigger the coupling loop is, the broader it's going to become, but also the more signal you'll have. With a very small loop like this, we're going to have a very, very sharp antenna, very sharp frequency selective wise, but we're not going to couple as much as we are
the Q of the inductor.
with a larger loop like this. So I'm going to tune to 540 on the receiver over here. We're already tuned to 540, but I'm going to put it in the center of the screen.
540 is like a ultra.
And I'm going to spread it out a little bit. Zoom in a little.
Shit, ultrasonic.
So here is 540 kilohertz. You see that tiny little nub in the middle there?
Oh, it's actually
right
like
in the middle of the screen. That's 540 kilohertz. Obviously, something that's 2 inches in diameter does not provide us with a very good antenna for the medium wave band, or the AM broadcast band. So let's couple this in. Let's put it right in the center And we'll watch on the screen as I tune across. Here it comes. You can see the the selectivity moving back and forth here. Okay, so there is. In fact, let me unmute this so we can hear some. Maybe you'll be able to hear. I don't know. It's very, very difficult doing this from the other side of the room. Now here's something too.
I don't know if that's a tuning capacitor he's using. It doesn't really tell you.
That's when they take the small mouse. Okay, let's orientate this towards the station so we'll be able to hear it. All right. So, see, that's a little bit quieter. That doesn't have all this noise. And I'll bring it down here.
Well, right now we've got a cloud agency chop rate.
A 2-inch loop. But what I'm using now is a coupling, a threaded coupling, and it provides a very, very nice, smooth way to orientate the loop. Let me just grab one out of my box of cookies over here. Hold on a second.
His box of cookies. His backs of cookies. Not his box of cookies, but his backs. Gabriella Drake Shadow
anywhere
UFO.
at Home Depot or anywhere. I'm sure even around the rest of the world. Basically, it's just a threaded coupling, which
Yeah.
which
I got a few
threads
of
into
those.
itself. Okay, and
Where's the
it's
loop
nice and
go?
tight too, and loose enough, tight enough so that the antenna doesn't wobble back and forth, but loose enough to provide you with a nice smooth.
Mounts
This
nice.
is why you see crystal ovens that run way, way above ambient temperature. So even if it gets warmer in the room or colder in the room, the temperature of the crystal stays the same. Part of the spectrum, right? So here in Inmarsat, and we built a circular polarized helical antenna. This one happens to be right hand. But I ran into a few issues that are kind of generic to the problem. Or any time you are experimenting in sort of an unknown part of the spectrum, right? So here we are at 1600 megahertz. That's 1645, right? 1.6 gigs. And I'm not sure if I'm pointing at the satellite, at the right satellite. I'm not sure if my receiver's working at those frequencies. I'm not sure if my antenna's working at those frequencies, and I'm not even sure I can get reception. So you have, one of the problems is you have so many variables, and when you have multiple variables like that, you have to come up with something like anything. But this will allow you to put your radio on the right frequency. Go up to 1600. I think 1600 is something. Okay, so there you can see this is a run of the mill 50 megahertz clock. Okay, and this pin right here, this one is just the lead of the socket tilted up and then with another inch of wire on it. And over here, it's just an SMA connector soldered to the board.
Is that an antenna?
And then soldered again there, and then the insulation
Coupled?
comes up here. Okay, so it's probably 2 inches long, something
That's
like
like
that.
a capacitor?
One thing you have to really be careful about is you don't want this wire, the output of this clock, to touch this wire. You want an air gap in between those, okay? You want the RF to couple through, but you don't want any DC or those really big signals. Typically, this is like, 3, 4, 5, 6 volts of peak to peak. So you don't want that touching, but you do want the air gap. And this thing works out really well for a couple different purposes. Okay, so there's the, one pin bypassed with a capacitor. Boy, am I not very steady here. Bypassed with a little tantalum to ground. Minus goes to the circuit board. This other pin of the 4 pins is soldered to the circuit board, and then the last pin is lifted up.
This is called a comb generator that he's working, so it generates frequencies across a band for
Okay, just lift it up with a piece of wire
calibration,
connected to it.
maybe,
And
whatever.
so even though this thing fundamentally says, doesn't say that, says 50 megahertz, it's spraying out all sorts of interesting garbage. But 50, 100, 150, 250,
Those are
4, 5, all the way up
harmonics.
to, I tested it up to 650 megahertz. So this is your reference, okay? Now the other thing is, you can take this.
Oh,
Let me
okay.
zoom back down.
I see what he's talking about. Instead of connecting it directly,
My finger's in the way.
he's just letting it
Sorry
float.
about that, folks. You could take this.
If you connect it directly, it cuts out all of
and
the
then you have this
harmonics.
connected to your receiver, and you can literally use this as your source and this as your antenna. You know, if you're working in the, you know, looking for the Inmarsat stuff, to find out, holy cow, my antenna does work. You know, I can wiggle it around and move it and see that it's actually working. So now you have confidence that your antenna is working, your preamp is working, you're roughly tuned in the area where you want to be.
Ingenious.
Okay, so I'm going to go over to the other room and we're going to set this up at the ham station. And first thing we'll do is we'll turn it on from cold, and you'll see how drifty this is. Again, this is not a frequency reference. This is just hanging out there, making approximately 50 megahertz, and it's rich in harmonics, and we're going to take advantage of that.
It doesn't.
Okay?
It's not stable
So,
when
catch you over
the output's
at
not
the
connected.
ham station.
Temperature? It says no. Mikey says, please subscribe to my grandpa's video, yada, yada, yada.
And we're going to be using SDR console just because it's easier. It's kind of easier for me with my limited software experience to move around the band. Okay, so let me set that up. One other thing, when I say I'm putting my finger on it, I'm putting my finger here.
That's changing the
And
temperature.
that temperature from my finger transmitting into the crystal inside here, you'll see the drift immediately. Oh, the other thing to remember is that if this thing is not 50 megahertz, let's say it is for a second. Actually, let me sit down here.
Yeah, have
This
a
thing is
seat,
on
Pete.
50 megahertz. So what would you expect the second harmonic to be? 100. The fourth harmonic, 200. The fifth harmonic, 250. But suppose it's not exactly on 50 megahertz, like it's not here. Say it's 100 cycles high or low, but we'll use high because I can do the math then. At 50 megahertz, it might be 50.100. At 100, it's going to be 50.200. At 200 megahertz, it's going to be 50.400. And so by the time you get up to the 32nd harmonic, up around 1600 megahertz, it's going to be off 2 or 3 kilohertz. But not a big deal. At least now you have a reference, something that you can look at and something that, you know, you could sort of depend on. The other thing you'll see when I put my finger on there, my finger is going to be warmer. 450, so 550 hertz low already. I have to move up in frequency instead of down. Let me zoom out a little bit. Point is, right now, that we have an oscillator.
All right, that was nice to learn.
Here was out of just crummy components, and that it really didn't have a high Q, which meant that it was going to, here's an example of it. I'll show you these up close. I got some pictures. So the notch, and he said, geez, he's got a huge AM station, a mile. The question is, well, how will this play out? Like 12 or 13 bucks straight out of China. Consists of a noise generating diode that's reverse biased, and then a bunch of MMICs to bring the level up to something that we can work with. So what does a noise generator do? Well, we certainly don't want a noise generator when we're receiving things, but this noise generator has a broad spectrum. from maybe 10 kilohertz up to 50 megahertz. I don't remember the exact specs on this. You can go on eBay and find all sorts of different ones. They'll give you the specifications for it. And the noise generator creates just that. Creates around an S9 noise level. Nice and flat. Okay? So that anything you put in the path between this output, this SMA output, and the spectrum analyzer that you're using, whether it's a spectrum analyzer, and then we'll take a look at the high pass filter I made, and then we'll take another look at the low pass filter that I made. Notch filter. It really is horrible. It's just a loop stick with the appropriate number of silver micas on the side here, the capacitance value to get it to notch around 610. And really, the Q of the system is low, and you'll see that when we go through the spectrum analyzer. And then, of course, the W1 VLF low-pass filter. I threw this together. We're going to do a peak hold on that one. Whoops, I was in the wrong one. 60 or 70 dB of difference there. So what's next? Next thing is I'm going to take the AM high-pass filter, and we're going to put that in. And I think it's going to start to roll off down, eliminating the AM broadcast band around 17 to 1800. I don't remember this filter, that number 2. Now I'm going to insert the high pass filter. Okay, and you can see, and now we're going to do an average on, an average on that. Okay, we're smoothed it out. How much did we smooth it out? Well, let's see. We're only smoothing it out by 2 averages.
No, that's all from that SDR control that he's using.
Give you the specs on it. It'll be plus or minus a couple of. Oh, okay. The start is at 600. Is at 0 kilo. I got this idea from a searchlight that I noticed you could see from.
Okay, I'm not particularly advertising this dude's website, but anyway, I learned about using the crystal as a comb generator. Okay, that's fine. The noise generator, I mean, I can make noise generators, but the circuits themselves are going to have noise. I guess use diode. You can use a diode. He said MMICs in there to multiply the frequencies and add the noise to the frequencies, and lo and behold, you've got a noise generator. Where is my other site here? Okay. Did I delete it? I'm on the web page. It still should be there. What the hell did I do? Oh, here. Let's go over here. Noise. I'm not going to spend $10 on a frickin' noise generator. Portable white noise machine. Not they're only up to $20. I don't even have anything. Let me type this in. White noise signal generator kit. Signal generator. I actually have that kit. I just got these. These kits are like, they're like $10. You've got frequency generators. All kinds of crap here. Frequency generator for healing, huh? Resonance generator, 7.83 hertz stability. Yeah, there's a thing about the earth noise. Schumann wave generator, 7.83 hertz. Okay, so this is a scalar antenna. And I want to build a scalar antenna and somehow use that antenna. Here's another one here. That's a square one and a round one. They want $20 for this thing. They've connected a little oscilloscope to the thing with a bunch of buttons, and all it is just a circuit trace that goes around in a circle. That's just 200 kilohertz. That's interesting. In fact, that's really interesting. I gotta get to work on my SDR. I got all kinds of programs, all kinds of software. The SDR looks across a wide band of frequencies to find out if there's any signals, and that's what we need. It would be nice to have something like that instead of just having to listen to broadband noise, because we need to filter it optically, and then filter it electronically, and all kinds of other good stuff. I think it's gonna work. I'm just trying to grab these stupid website here. God almighty. Oh, come. Let's see here. Wait, I didn't get the number. There we go. I'm just on Amazon taking a couple looks at the scalar antenna idea type of deal. I've known about this stuff. I just haven't done anything with it. There's another one here. I think that's it. So like basically I need to work on my voltage sources. My LEDs are all ready to work with. My tuning cavity is, for all intents and purposes, ready to be used. And then all I have to do is build a connector for the little lens that goes on the end of the tuning cavity, and so on and so forth. I am done for the night. It was an interesting research night because I didn't really want to do anything with my setup. I've got a lot of stuff. I've got all kinds of wire, all kinds of coils, all kinds of inductors, ferrite cores, capacitors, resistors. I've got those. I want to build that frequency comb generator like he's got it designed there. I got those. You can just hook that up to 5 volts, but he took the DC off with the capacitor or something. I don't know what he did there. Yeah, that's what it's all about. I will say have a good night, and I shall return.